The last type of machine we have C is DC series motor or series DC motors, and from the name we will connect the field and the armature in series. So here is the armature, EA, RA. Here is the field, RF. So what we will do, we will connect the field in series with the armature. So here is V source. So the current I source is the same as the current going into the field is the same as the current going into the armature. Because you have a series connection. Okay, so just I'm sketching it like this so you can see the connection, but you can just sketch. So you can just sketch RA plus RF, and then you have your armature, and here you have a battery. So this is totally correct from the electrical perspective. But as a electrical machine guy, I always sketch the field making a 90-degree with the brushes. Now the equations we have in terms of machine equations, EA equal to K motor I field omega, or equal to K motor IA omega. And as you can see, we replaced IF with IA because IA, IF, and I source are the same because of the series connection. T developed equal to K motor IF IA or K motor IA square. And this is the beauty of this machine, okay? So the current IA is what you invest, is the current you give to the motor. More current is more investment, more money you pay. And think about the current for all the motors from here on as the gas of your car. Putting more gas, you are expecting more acceleration and more torque. And this machine is giving you a torque that is proportional to the square of the current, or the square of the gas, compared to the torque in this case is proportional only to IF because to IA, because IF will be constant. And also in the separate case, the torque is proportional to IA. So this machine is the only machine that has a torque proportional to the current square, which means it is giving you a crazy torque. Okay, this machine is the most powerful machine, and we will see when we study its applications. And the last equation is T developed omega equal to EA IA. So the only change in the machine equations is we use the fact that IF equals to IA due to the series connection we have. In terms of circuit equations, we have 1 KVL V source equal EA plus RA plus RF IA, because we have a series connection, and I source equal IF equal IA. This is the second equation. So this is KVL and this is KCL. And these are the only equations we have for series machine. And if we sketch the power flow diagram, so the input power is V source, I source. This is Pn. Then we lose IA square RA plus RF. The remaining power is the power going to EA, so it's EAIA, which is T developed omega or P developed, the developed power. Then we lose some mechanical losses, and then we have our P output net or net output power. So the power goes from V source I source, then we lose power in RF and power in RA, so which is IA square RA plus RF. The remaining power is the power going into EA, so this power is EA IA. Then we lose some mechanical losses in the shaft, and after we subtract the mechanical losses, we have our output power net going to the mechanical load. If we need to find an expression for the percentage efficiency, it is P out over Pn multiplied by 100%, and this is the percentage efficiency. And here we can see P out and Pn. And this is the third or the fourth type of machine. So in this part, we covered the series machine or the series motor, the shunt motor, the separate motor, and the permanent magnet motor. And these are all the types of DC motors. Before starting solving examples, so we will solve examples in this lecture and the upcoming lectures, so I need to define some important operating points before moving forward. In the operation of motors, we have two important operating points. One point is called no load, and the second point is called starting. Okay, so these 2 points or these 2 operating conditions are very important: the no load operating condition and the starting condition. So let's start with the starting case. So if your motor is starting, what does this mean for you? So if you are solving a problem, and is a problem we are saying that at starting blah blah blah, so you know that the motor is at starting. So if the motor at starting, it means its speed currently is 0, and if the speed is 0, EA is K motor IF omega, so EA is 0. So this is the meaning of starting. So to study the motor at starting, you put EA as 0. So at starting, this is what does this mean, that EA is 0. At no load, so no load means your P output is 0. No load. Okay, so no load means the output power is 0, which means you took out the motor from the box and you just plugged it into the electricity, so it is freely running. Or if you think about your car is parked and you have your gearbox at N, at the neutral. This is what is meaning by no load. So no load doesn't mean that it is not running. Okay, so if your car is at N position, so your engine is running but not coupled to the wheels. This is the meaning of load. So no load doesn't mean that the speed is 0. It means that the torque is 0, the power is 0. So at no load, the power is 0. So if you look at the power flow diagram here at this branch, so if we look at the power flow diagram, we have P developed, we have mechanical losses, and we have P out. So at no load, this P out is 0, which means that P developed equal to the mechanical losses, and P developed is EAIA equals to the mechanical losses. If the mechanical losses is 0, your EAIA will be 0. Okay, so this is what does this mean, what it means when we say you have a motor at no load, so EAIA equal to the mechanical losses. So if the mechanical losses are zero, in this case EA IA equals 0. Don't forget that speed is not 0 as we mentioned, and EA equal to K motor IF omega, so this term is not equal to 0, so the only variable here can be 0 is IA, so IA will be 0, which means at no load the input current to the motor will be 0 if you don't have any mechanical losses. Again, if we go back to the car example, if your car is stopped and your engine is running, but the gearbox is at neutral, you still take gas to run the engine. So you still take current, so you still take some current to run the motor if it is a motor, or you still take some gas to run the engine if you think about your car. But if your car engine is ideal, it should take 0 gas when you are just idling. You are running the engine without attaching the engine to the brakes, to the wheels. So if the engine or the gearbox is at neutral, you should consume 0 gas if it is ideal, which is the case here. So if you have a mechanical losses at no load, IA is not 0, but it will be small for sure. So the motor will take some current to get over the mechanical losses, or to overcome the mechanical losses. But if the mechanical losses is 0, IA will be 0. And these are very important remarks for motor operation, is starting at no load. So starting means IA equals 0. No load means EAIA equal to the mechanical losses. So if the mechanical losses is 0, IA will be 0 at no load. If the mechanical losses is given, you will have an extra equation that EAIA equal to the given value to you. So let's solve our first example, which is it's DC series motor. So I posted online some solved examples for DC motors, and we will go through these examples in the upcoming lectures. So let's solve this example. We have a DC series motor. So most of the students will lose marks while they are reading the question. So let's read the question together and extract the information. So we have a DC series motor. So I will start by sketching the motor. Okay, let's just remove this. So I will start solving this problem by sketching the motor. So here we have the field in series with the armature. EA, and here T developed, omega, RF, RA, V source, I source, IF, IA, and we said that all these currents are the same due to the series connection. And the motor is operating at full load. So full load is the same meaning as rated, and this is the value written on the motor. So if you have a motor and the nameplate is saying that this motor is 100 volt, 10 horsepower, so these values are called full load or rated. So the supply is 240 volt supply. So the source here is 240 volt. And the motor is running at 600 RPM. Okay, so please divide the given data into cases. Okay, so let's say this is case 1. So case 1, V source is 240 volt, and speed, your speed is 600 RPM. We will use n small as the variable for, or the symbol for speed. So N equal to 600 RPM. The back EMF, so the term back EMF is EA. So the back EMF or EA is 217.2. So EA equal to 217.2 volt. At a line current of 38 ampere. So this current, when we say line current or motor current or source current or input current, all of these are referring to the current coming from the source. Okay, all of these are referring to the current coming from the source. So this is I source. So in this case, I source equal to 38 ampere. And because we have a series connection, this is IA and this is also IF. Here we need to find the armature resistance, assuming that the field resistance is 0.2. So for DC motors, the problem is so simple because it's just DC. No complex number calculations, no magnitude and angles, no active and reactive. So simply if we apply KVL, V source equal to EA plus RA plus RF IA. So this equation is simply KVL. So we are doing KVL around this loop. So V source in our case is 240, EA is 217.2, RA is unknown, RF is 0.2, IA is 38. So the only unknown in this equation will be RA or the armature resistance. So we can find the armature resistance from this equation. So RA equal to 0.4 ohm, which is the first part here. Then we need to find the no load speed, okay? So we need to find the no load speed. Given that the no load current is 1 ampere. So why the no load current is not 0? Because there is mechanical losses. So now we have another case, let's name it as case 2, and this case 2 is a no load, and at no load we know that our current IA in this case, let's name it as case 2, equal to I field in case 2 equal to 1 ampere. So what we need to find at case 2 at no load, we need to find the speed N2. Now, is there any statement here about the source voltage? Have he changed anything about the source voltage? No, the source voltage will be constant unless it is stated in the problem that the source voltage is changed. So let's see how we can deal with this case. So we will say, okay, V source, which is 240, equal to EA in case 2 plus RA is 0.4, RF is 0.2 multiplied by I armature 2. So here we have the only unknown in this equation because I armature 2 is 1 ampere as given. So the only unknown in this equation will be EA2, and EA2 is 239.4 volt. So the voltage in this case, E armature 2, is 239.4 volt. Whenever you are asked in DC motor questions about speed, you need to calculate EA. Whenever you are asked about torque, you need to calculate current and vice versa. So speed and E are coupled. Torque and IA are coupled. So how from EA we can find the speed? So if we go back to case 1, So for case 1, we have the following information. EA1 was 217.2. I field 1 was 38 amperes. And the speed N1 was 600 RPM. So what we can do, we can say EA equal constant IF N. Someone will say, no, we learned this as K IF omega. So the relation between omega and the N is the conversion from radian per second to RPM, which is 2 pi over 60. And this is constant, and just this K will change. So the unit for K here will be volt per ampere RPM, not radian per second. So we can find the constant for the motor. So we can say EA 217.2 equal to K, IF is 38, N is 600. So we can find K, and the unit for this K, so let's calculate this K, 217.2 divided by 38 multiplied by 600. So this K is 9.526 10 power negative 3 volt per ampere RPM. Now if we go to case 2, EA equal to 239.4 equal to K, and the K is constant, so same K, multiplied by IF2 multiplied by N2. So K is 9.526 10 power negative 3. IF2 is 1 ampere multiplied by N2. So the only unknown here will be N2. So N2 will be 25130.38 RPM. So this is the no load speed. So the no load speed is 130.38 RPM, and this is what is required. So we can get from case 1 what is the constant for the machine K, and it is the constant for the machine, so we can use it at any operating condition. Or someone will say, okay, EA in case 1 is K IF1 N1, and EA in case 2 is K IF2 N2. So if we divide the two equations, we get this famous relation, which will be in the formula sheet. EA1 over EA2 equal I field 1 divided by I field 2 N1 divided by N2. So this is one of the famous relations for DC machines that you can use directly, and it will be in the formula sheet. So EA1 was 217.2, EA2 was 239.4, IF1 was 38, IF2 was 1, N1 was 600 RPM, and N2 is the unknown. You can find N2 to be 130.38 RPM, which is the same answer. So what we had here, we had a DC series motor. So we had a motor, and this motor is connected as DC series. So this is a DC series motor, and we solved this motor when the motor was coupled to its rated load, and then we solve it again, the same DC series motor, when you removed the load, no load. And this can be done by just having a clutch here, and you disconnect the clutch so you can remove the load. When the DC series motor was running with full load, it was running at 600 RPM. When you completely removed the load, your speed went to 25 kRPM. Okay, and this is a big issue with DC series machine. So 25k RPM, this is almost infinity, which can break the bearing and can damage the mechanical system or the mechanical structure. So this speed is very high speed. Okay, so this is a big issue with DC series machine. So the no load speed of DC series motor is almost infinity, and we will prove this later on. And this machine has to be operated under load. So we have to operate DC series machines under load. No one will operate a DC series machine at no load. Okay, so this is our first question on DC, and we will solve many questions on DC machines. So I will stop the video here.